In my last video, which is called Do All Objects Fall at the Same Rate, I tried to derive under which assumptions all objects fall at the same rate and how the exact result looks like. And I derived in this video this differential equation, which is basically the two-body problem. So we have here the mass of the Earth or some other mass, and in a distance r, different mass which has the value small m. And in the previous video I derived how the acceleration is connected to the distance and the masses. And now we are going to solve this differential equation. So our goal is to get an information about how this distance is going to change with time. The first step in solving this is rewriting this expression here to reduce the order of the differential equation. And this can be done by rewriting the second time derivative in the following way, because we know that a dot means time derivative, so this is nothing else but this here by definition, and the differentiation with respect to t can be replaced by the differentiation with respect to the coordinate r, because it depends on time. So it's the chain rule we apply here, and we can write down this, and this vector is simply r dot. And in the next step we insert this relation, the right hand side, here, and we separate the variables. So on the right hand side we would like to have something which is only dependent on the coordinate r. So on the left hand side we will have dr, and on the right hand side we will have something which is only depending on the velocity, so r dot. So we will have r dot times dr dot. Having now this equation, we can integrate. So on the left hand side our integration limits will be from the initial radius r0 up to our final radius, let's call it r. And on the right hand side we start with a velocity r0 dot, and we'll end up with a final velocity r dot. And here we assume the starting velocity to be 0. So initially we assume the initial speed of the objects against each other. So at t equals 0 we have r0, and at t equals 0 both could have a finite velocity, which is given by the time derivative of the distance between the two objects, but here let's assume that this is simply 0. So we end up with the following two integrals, and both of these integrals can be solved easily. And I incorporated the sign here into the limits of the integral, and solving this and this integral leads to. And since we assume the initial velocity to be 0, we have on the right hand side only r dot squared divided by 2. In the final step, we will bring the 2 on the other side, take the square root of this equation, and then we are left with dr over dt on the right hand side, and we will separate the variables, so we will bring the time on the left hand side and have the coordinate r on the right hand side. By taking the root, we can have two different signs, but here we know gravitation is attractive, and in this case is a case where the distance r between both objects is reduced with the time, so r dot is in our case always smaller than 0. Thus we need here a minus. So let's sort now the variables, separate them, and let us give this prefactor here a name. Let's say it's gamma. And in this form we can again integrate on the left hand side, integrate over the time t, and on the right hand side integrate over the coordinate r. The integral on the left hand side is trivial, and on the right hand side this integral is a little bit more tricky, and we have now to solve this, and having the result for this integral we are done and can write it down at least in the form where we have on the left hand side our time and on the right hand side some function which depends on the initial distance and the coordinate r at a certain time t. So in the last step, let's solve this. On the left hand side we have t times gamma, and on the right hand side let's rewrite this form a little bit in a different way. Now, having it in this form, we can further simplify this expression by introducing new coordinates. And so let's rescale the distance by defining a distance which is without units, and it will be defined by the distance divided by the initial distance. And let's define a time which is also not in units of seconds but in units of 1, and this is gamma divided by the initial distance times the square root of the initial distance times t. So it's nothing else but a rescaling of the two variables to simplify this expression, because using the substitutions we end up with the following equation, which is now this here, which is now much easier to handle. So the last task is to solve the integral on the right hand side, and due to the substitution we start with 1 and have to integrate up to r tilde. We solve this integral by using a substitution. So the first substitution is we replace radius tilde by sine squared, because this will give us here a cosine squared, and due to this replacement we have for the differential sine y times cosine of y dy, and this expression can be simplified by sine of 2y dy. And let's plug this in, and the result is this form. So this is due to substitution, so this is this part here, and this is simply sine squared of y, because we have here r tilde to replace, and 1 minus sine square is cosine squared. And for the boundaries of the integral we have to take the inverse function of this one here, and let's further simplify this expression here. This is tangents squared, so when we take the square root we end up with the absolute value of tangents of y, and now one should check whether this expression, this factor here, can be negative. But we don't need to worry about the sign here, since our integration will be from pi half. So this is the arc cosine of 1 is pi half, restricting of course the angle to be between 0 and 2 pi, and the other limit goes to 0. Since the distance is getting smaller and smaller, and arc cosine of 0 is 0, and the tangents is positive between 0 and pi half, so we can drop the modulus here. Using now in the last step trigonometric relations which simplify us this argument here, using this relation we plug it in and get the following integral, and we can write down the standard integral, so the result of the standard integral. And that's it. So now we are left with inserting the boundaries of the integral into this term and simplify it a little bit. Okay, let's recall what we have. On the left hand side we have the rescaled time, so t tilde was the time times gamma. Gamma was square root of 2 times the gravitational constant times the sum of the two masses divided by the initial distance times square root of the initial distance. And the distance tilde is the rescaled distance, rescaled by the initial distance. Okay, when we plug in this integral limits, we get the following expression. And this expression can be simplified even further. So let's look at this part. This is exactly the arcus cosine of square root of r tilde. So arc, including of course, so this sign here. So we have arcus cosine of square root of r tilde. And this expression here can be simplified by first recalling that sine of 2 times something, let's call it w, is 2 times cosine of w times sine of w. This means that when we plug in arcus sine into these two arguments, sine and arccosine will cancel each other, and cosine of arcus sine will simplify to the following expression, which appears when we rewrite cosine as square root of 1 minus sine squared. That is this expression where now we have replaced cosine with this function here, and we are left with sine squared of arccosine, and this will give us here the modulus of r tilde, because square root of r tilde. So this is our final expression for the formula which tells you, given a certain distance r tilde, which time passed, which time t tilde. But what we need for a simulation would be to see the dependence of the distance on the time. And the problem with this expression is that one cannot rewrite it simply into this form. One cannot solve it for the distance r, but we can look at the extreme cases. So the extreme case is when r tilde is close to 1, and then the other extreme is when r tilde is close to 0. So what one can do is to expand this in a Taylor series up to a certain order, and then solve it for the distance r. And let's do it first for the case where the distance is close to 1. And I will only give the result. So in this approximation, t tilde of r is approximately 2 times the square root of 1 minus r tilde. Let's forget about the modulus, because we assume only positive distances, and this allows us to rewrite it in this form, and we get finally this equation here. And putting back, undoing the rescaling, we end up with this formula here. And we see immediately that this equation is the free fall of an object where the acceleration here is due to gravity g, so it's the small g, but with the difference that here we really take into account the mass of the falling object divided by 2. The other extreme is, of course, the case where we are close to 0 with the distance. To 0 means the ratio between the distance and the initial distance is close to 0. In this case, we get the following result. And here one could ask, why does P appear here? And this can be understood by asking the question, how long does it take for the mass centers to collide? So we have the two masses with the centers, and here we have the distance r, and at some point, of course, the surfaces meet, but we don't take them in this approximation into account. We really assume point masses now, and we ask how long does it take for these two centers to collide. And this time is given by the integral where the final radius is now, not radius, but distance is now 0. And we simply have to look back in our previous solution of this integral and see that this is given by the arccosine of 1, and this is pi half. And this is how the pi half enters here. So when we take out the 2, we have pi half minus t tilde. So putting the normal scaling back, we have this result here. But of course one has to be careful, since we assumed now the masses to be point masses, so the centers can come as close as 0, but let's, for example, assume that we shrink the Earth down to a very small radius. Then it can happen that we squeeze it down below a very critical radius, and this is the Schwarzschild radius. And for example, for our Earth, the Schwarzschild radius is about 9 millimeters. Our classical picture breaks down, and we have to do the calculation with the math derived for the curved space-time. Finally, I would like to show you the numerical solution for the equation distance depending on time, which is plotted here in the blue curve. So the blue curve gives you the distance between the two objects at a certain time. The time is plotted on the x-axis, and both axes are rescaled. The distance is rescaled by the initial distance, which is here also r0, and the time is rescaled by a factor which is to give you a feeling, let's take the mass of the Earth alone and divide it by the radius of the Earth to the power of 3/2, and let's take the inverse to get the feeling about what is the characteristic time. And here we get approximately 9.5 minutes. What does this mean? It means that if you have a very small light object, so this is the mass small m, which is much smaller than the mass of the Earth, and you let it fall towards the center of the Earth, and let's say the Earth is a point mass with the mass me, then after approximately 10 minutes, that's here where we have 1, after 10 minutes it has reached approximately 0.7 times the radius of the Earth. And here, after pi half times 10 minutes, both objects would collide, so both point-like objects. Finally, you see here the red curve, which is given by our first approximation. So when we Taylor expand up to first order for radius approximately being r0, and the green curve shows the second approximation for the case where both point-like objects are very close to each other. So I hope I could give you a nice view into the mechanics of the free fall. Thank you for your attention. See you next time.